Greetings and welcome once again to my new calculus channel. My name is John Gabriel, and today I'm going to explain to you what is a differential. Now, I know I've talked a lot about this in the past, but I've been quite worked up because of the stupidity of mainstream academics. So today I'm just going to relax, and since I don't have a time limit on me because I've got this free screen recorder, I'm going to speak slowly and try to explain this to you in the best possible way I can. Now, there is no good video or good article on the internet about what is a differential because nobody I know in the mainstream knows what is a differential, and they don't even know what is a derivative. So those are big statements, but I'm about to show you now once and for all, and you'll understand exactly what's going on if you keep an open mind and you pay careful attention to what I'm about to say. So let's begin. Now, if you do a search, you can do any search on the internet. First of all, let me just see if I'm still recording. Yes, I am, so all is fine. Okay. If you do a search on the internet, you'll see a lot of garbage videos. This one in particular here defines a differential in terms of itself. So it says dy is equal to, or in terms of another differential. So dy and dx are differentials, but it's defined, one is defined in terms of the other. So circularity is a popular sport in mainstream mathematics academia because they're unbelievably stupid and ignorant, and they've never understood mathematics or calculus. In fact, a lot of these problems go back to the foundations. What are the foundations? For example, what is a number? What does dy and dx mean? And what and how did we get them? How and where did we get them? So Newton and Leibniz did not know what they were doing. They were groping around in the dark. Okay, if they're called the fathers of calculus, I must be the god of calculus because no one understands calculus as well as I do. In fact, no one ever has. So I'm about to explain to you what is a differential, excuse me, and also what is a derivative. So let's begin. Now, if we look at a straight line, normally a straight line like that always has a slope. Okay, even if it's vertical, it has a slope, not in terms of rise over run, but in terms of angle. Okay, so it's because of Newton and Leibniz that that vertical lines no longer have a slope. Okay, so no slope. But it's only no slope in terms of rise over run. There is a slope in terms of angle, and that slope is pi over 2 radians, or what most of you will know as 90 degrees. Okay, so now what you have here is just a finite difference when you calculate the slope. So what is this finite difference? It's just the difference in y values between this point and this point. So this is dy and this is dx. Okay, now dy and dx are just symbols for numbers. Yeah, that's all they are. And in fact, they are differentials, but they've got nothing to do with infinitely small values or infinitely large values or any of that nonsense that you find in mainstream mathematics academia. Also, no change is happening. As you can see along here, nothing is changing. If you decide to take the slope here, it's exactly the same, or here, or here, or here. Doesn't matter where you take the slope, okay? Nothing changes. The slope of a straight line is always constant. Okay, so now, because mainstream mathematics academics do not understand the concept of number, they've resorted to all these hand-waving so-called explanations. Now, what happens when you have a nonlinear curve and you find the derivative. Well, very simply this and nothing else I'm going to explain to you. All that happens is this, is that you're finding an expression which describes the slope of this tangent line at any point along this curve, okay? So that's all it is. So the derivative is simply the rise over the run in general expression, and dy and dx are finite differences. So dy, for example, is either proportional or equal to f of x. Now, you have to be careful here, because in mainstream calculus this isn't true, but it's true in the new calculus, okay? It's equal to f of x plus n minus f of x minus m, where this is x, okay? And dx is equal to m plus n, right? So these are called differentials. And why are they differentials? Because if we look at a ratio, any ratio, or supposedly the derivative dy dx, as I've written down there, it doesn't have to be any particular fraction. It can be many fractions. So let's say that we've calculated the slope of this tangent line, and that the slope of that tangent line is, let's say, 2/3, whatever, okay? Then, and we write dy dx is equal to 2/3. Now, what this means is that any equivalent fraction to this will also be a derivative. And we can find differentials, we can find equivalent differentials to 2. For example, 4, and in this case, 6, right? And we can find a lot more. We can find, let's say, multiplied by 5, that's 20 over 30, which is basically the same as multiplying that by 10. Okay, so dy and dx are symbolic numbers, okay, or magnitudes. Magnitude is not a number, by the way. That's very important, okay? So a magnitude is just some distance that cannot be measured exactly, okay? An incommensurable magnitude. That means a magnitude that is incommensurate with any other. So let's take this again. What is a differential? A differential is just a finite difference, okay? So this here is just a finite difference. That's all it is. It's not an infinitesimal or any of that bullshit that you hear from your math professors or you read in thousands of textbooks. It's got nothing to do with infinity. An infinitesimal doesn't exist. It's a garbage concept. Infinity is a garbage concept. And the theory of limits is not even required in calculus. And so why is the theory of limits not required in calculus? Well, because neither of the so-called fathers of calculus understood that f of x plus h minus f of x over h is equal to that plus q of xh. Now, what you're seeing down here, folks, is my historic geometric theorem of January 2020. This here, by the way, is the same as dy dx. Okay, so neither of the so-called fathers understood calculus. Otherwise, this is what they would have come up with. And I explain this in an article called My Historic Geometric Theorem, which I will place a link to in the details section. So now we know what is a differential. These are called differentials. And yes, you can multiply them just as you would a number, or a magnitude, because that's what they are. So for example, if you say pi times 3 squared, you're treating this here as a symbolic number. Okay, it's not actually a number, it's an incommensurable magnitude. It's actually more appropriately defined as a constant. Okay, it's a constant. Whoops, nothing to do with these constants. Okay, now, so it's a constant, and we're treating it just as we would a number, and that's the same way you handle variables in algebra. If you say x times 3 squared, this here is a constant, and by the way, it's not a variable if we say something like that. Okay, it's not a variable, it's actually a constant. And what is it equal to? Yes, it's equal to 1, okay, because only 1 times 9 is equal to 9. So there are a lot of flaws in mainstream mathematics, a lot of wrong terminology, and that's why students get confused. So these particular symbolic representations are differentials, and the fraction dy, the fraction of one differential to another differential, is called a derivative. Okay, derivative. And actually all it is a slope. That's all it is. A derivative is a slope. This and nothing else, by the way. It's got nothing to do with rate of change or instantaneous rate of change. There is no such thing as an instantaneous rate of change. The tangent lines along this curve have never changed in past perpetuity, and they're not changing now, and they won't change forever and ever. Amen, so to speak. Also, neither x nor y changes in any particular function. Oops, I didn't mean to do that. In any particular function, if we write f of x is equal to x squared, nothing's changing there, okay? A certain set of x's, which is called the range, is mapped on to y's, which is called the x's, which is called the domain, is mapped onto the range, which we normally call y's. So nothing is changing there either, and even in this case, I reject that we should call x a variable because it's not a variable, okay? And similarly, if we write x plus 1 equals to 2, x is not a variable in that, is it? X is a constant. In fact, it's a number. It's the number 1. Okay, 1 plus 1 is the definition of 2. So now, let's just clear up the screen a little bit here. So I've given you a very brief, now how did I do that? Where is it? Oh, there it is. Okay. Giving you, now why didn't it do that? Okay, seems like it doesn't like that. Let's try this again. Bring it down a bit. Alright, so as you can all tell, I've got this new device where I can actually write. It's pretty neat. Alright, so let's get rid of that. Whoops. No, it's not doing that properly. There we go. And that, and that. Okay. Nice clean board. Believe it or not, I still don't know how to use this Microsoft whiteboard properly. But I'll learn. Okay, so now, so what I've told you is that dy and dx and dz, etc. are all differentials. And differentials are simply just finite differences. And I don't even know why I'm using the word finite, because a difference by definition is finite. I mean, it doesn't go on forever, okay? So it's really just a difference. All right, that's what a differential is. It doesn't become infinitely small or infinitely large or any of that garbage that you hear in the mainstream. And then of course a fraction of any of these, dy dz, is called a derivative. All right. Now we also get what's called a partial differential. Okay, so if we write dy delta y dx, we call that a partial differential. And again, that has to do with tangency. I'm not going to go into that right now because that's not the purpose of my video. Maybe in a later video I'll explain that. I have produced 1 or 2 videos on partial derivatives. So this does not mean the change in y with the change in x. And actually I don't know how they write it. Yeah, they write it like that actually. Okay, so this is a fraction of partial derivatives. So Delta y written like that and delta x written like that are called partial derivatives. Partial differentials, I'm sorry, and the whole fraction is called a partial derivative. Okay? So now we've learned in this video that a differential is simply a difference. Okay, that's all it is. That's what the word differential means. That's what it comes from the word difference. Okay, and the derivative is simply a fraction of differences. So a derivative is a fraction of differences. And who do we have to thank for that? To summarize, we have Newton and Leibniz, who decided they were going to define slope in terms of rise over run. Now, if you watch some of my past videos, you can see that you can, if you use angle to define slope, then the range of every function, doesn't matter what function it is, will fall between pi over 2 and minus pi over 2. So, and if it's smooth, it will have a derivative everywhere, even if there is a vertical line there, okay? Because vertical lines have slopes, as I've explained to you earlier. So this is now the best video on the World Wide Web, and it's the best resource for understanding differentials and derivatives. If you have any questions, place them in the comment section. Just one question, or at most 2 questions at a time, because my eyesight is not very good, and I will try to answer them. And if you're not already a subscriber, please become a subscriber. Okay, spread the news of the New Calculus channel by telling your friends, talking about it on social media. I've also written many thousands of articles, and quite a lot of them are already on academia.edu. So if you type in John Gabriel followed by academia.edu, you'll see a lot of my articles on there. And of course, I have my YouTube channel, which is the one you're watching right now. Okay, so click like and subscribe if you haven't subscribed, and of course help me to have a peaceful retirement. I've had a very turbulent life. As you all know, I suffered from depression since the age of 5. It hasn't been an easy journey. So contribute at my GoFundMe site. I'll place a link to the GoFundMe link. Anything will help. I'm trying to basically accumulate $50,000, and if I do accumulate that much, I'll probably buy myself a tiny house, and hopefully, if I'm still alive and well, I'll divert my attentions to writing down everything I've learned. In other words, the many facts that I have yet to reveal to the world, by the way. I am a genius, and I think you all know that. I'm sometimes an unstable genius. Well, that's one of my thorns in the flesh. I didn't mean to indirectly reference Trump, who I think is a despicable human being, but I'm not going to go into politics right now. That's pretty much it. My name is John Gabriel. Till next time, this is the New Calculus channel. Goodbye, folks.